Don't hello. Yeah. Okay. Hello, everyone. Welcome to this session. Thank you for joining us. I am Mehran Kamkar. I'm an NLP data scientist, and today I'm going to present you one of my research which I did with my supervisor during my PhD studies, Dr. Makrehchi. The title is Content Tree Word Embedding. We did this research in 2015. A little old in this domain. You know that lots of things happens past 4 years, and it's our journey to starting and become familiar with the word embedding and text mining. First, I will start from our motivation for this study. Similar to other domains in the text mining, we are using vectors. We should converting the text to vectors, which the vectors are the native language for machines. And as you can see in this domain, in the text mining domain, we first converting the text document to vector space representation, and then using this vector space representations for machine learning algorithm for different tasks like classification and clustering. And the performance and computational cost of machine learning algorithms in this domain are correlated and completely depends on the document representation method that we are using. Yeah. Yeah, sure. Okay, the first approach, which is since 1954 in the market, is bag of word, which is representing a document with the words inside that. And this approach is generating one vector with the length of the vocabulary of the document, and each element shows the count of that specific word in this document. There are some other methods like TF-IDF based on this approach, or bag of n-grams, and all of these approaches are in the market since 1954 until 2013, which word-to-vec is represented by Mikolov, and after that, in 2014, we had the glove. Word-to-vec is actually representing a fixed size word vector for each word, and this word is coming from training a neural network, which in one architecture, this neural network is training by surrounding words, which are predicting the current word. I mean that we have assumed that we have a fixed size windows, which is moving through the text and trying to predict the current word based on the surrounding word. Or in the other architecture, which is a skipgram, it's vice versa. It's predicting the surrounding words between based on the current word. There are lots of pre-trained models which are trained, for example, based on the Wikipedia or Google News or such large corpuses. And they're presenting each word with one vector. And I can see the problem like that. There are some dictionaries for machines. Dictionary of words to vectors for each machine. And glove is similar to the word-to-vec if we look at this as a black box. But inside that, the theory and how it's generated is completely different. It was 2015 that we did this study, and these two word embedding was presented in the market. And in that time, there was some very famous examples which are based on the fact that these word vectors are capturing the global knowledge from the corpus. And the words which appear in common contexts in the corpus are located approximately to each other in the vector. And here you can see that the relationship between man and woman is similar to king and queen, the word vectors in that multidimensional vector space, or between the verb tense, or the relationship between the name of a country and its capital. We did one visualization. We generated this Radviz visualization based on the word vectors of these two groups of words. Some of them are related to the automotive industry, and some of them are coming from the fashion. And if we zoom into this group of words, you can see that they are separated. These are the car-related, and these others are the fashion-related word vectors. And you can see that we can separate them with one linear line. There was one specific word here, one dot here, which is somehow between these two groups, and this is the word model. This word was used in both of the contexts. One was related to the model as a model in fashion, and the other one was in the automotive context. And these two models are not referring to same model. But in the word vector and in the glove, we just have one vector for model. There are some other terms like Apple as a company, or Apple as a fruit, or BlackBerry, or Jaguar. And it was actually our main motivation to solving this problem and to generating some better word representations, to representing the document by that word vectors for the task of classification. And the main motivation was to provide a document representation that simultaneously using the global knowledge, which was coming from the pre-trained features, and the local context. If you have any question at this point, yeah.
You want to fine-tune the model the architecture that you propose to redefine the embedding so it's like closer to one other, for example, category that you want, or no, you want to have like two different like representations for the model and then like having it with two vectors. Like what is the
the approach here was to updating the word vectors based on the context. Then we are just modifying the word vectors and then using them to represent the document.
Providing the signal to somehow shift it in the space so it's like closer to the one category rather than the other one. It's like this.
Yeah, let me. I will explain you exactly. Okay. The solution that we use in this study was coming from this structure, which we call that document content tree. It's a semi-taxonomy representation. It's not actually a real taxonomy. It's a semi-taxonomy representation of the document, which shows the dependency between the terms in the document. And the generating this taxonomy is starting from here. Assume that we have the first word and the second word, and the first one is the root and second one is the child of the root, and the word C, the third one, wants to join to this tree. We are comparing the word vector of the word C with word A and word B and all other words in the tree, and comparing the similarity or distance or any measure that we can using. And in this study, we reached to the point that the correlation works better than cosine distance for this task. Okay, here we are comparing the word C with word A and word B. If the word C's vector was more correlated with word A, it will be the child of the word A and sibling of word B. Or if it was more closer to word B, it will be the child of word B. And here we have the algorithm, which is, yeah.
Like, so how do you, for example, they're correlated like 70%. So which one is the child and which one is the parent?
We are comparing the word C with both of
Word
them.
A is already a parent, then we're deciding that word C is whether it's child or not. Is that the
Yes. Yeah. It's a yes and no. And finding the maximum correlation and joining to that node.
I can add, I think what you mentioned was you compare the correlations between word C and A and B.
Yeah.
And then to whomever is closer, it would be the parent.
Yeah.
And word B is just another child because it's also very close to word A, right?
Yes, exactly. Yeah.
But how do you find out which one is the like child and which one is the parent? Where do you get this prior assumption?
We are starting, we should discuss about that, but we are starting from the first word in the context. And for the third word, we assume that the first word is the root, the second one is the child. And from the third one, it will start generating the tree. Yeah. Here you can see that the first word is the root, the second word is the child of the root, and for each word in the context, it will compare the word with each word in the content tree, and then calculating the correlation, and the parent will be the word in the tree which has the maximum correlation, and then the word is going to be added to the tree, and we go through the next. Here I have one example. Okay, this one is generated with the same issue, with the same algorithm, which is one given a sentence, it generated this tree from that. The key idea of this algorithm and all this study was to updating the word vectors based on the location in the content tree. I mean that in this algorithm, when we are just creating one content tree, but we are not using this content tree. The point is that we are updating the word vectors while it's joining to the tree. And the word vectors will be updated with this formula, which is a weighted average between the child and its parent, the selected, actually, parent. And we have one factor here. We call this decay factor. And I will explain in the results that's how effective was this decay factor, which is showing that how much this the new generated word vectors be close to the parent or more close to the child. And this is the formula to updating the word vectors. And this approach actually is considering the influence of the parent's word vector to the new word vectors by updating them. And this is the general form for the word vectors. Assume that here we have the word in the level of n. And you can see that the previous word, which was its parent, was Cn-1, and the Vn is the current word vector. And if we continue this more and more, you can see that at the end we have the vector of the root, and this vector is can influence all the word vectors in the document. And I should confess that the weak point of this algorithm is that this root is selected randomly or selected as the first word in the context. Any question?
Why? I guess it's a linear combination that you try to update it based on a linear combination based on this decay factor. Was there any reason for why it should be linear? Because you have this assumption that's already like projected in a Euclidean space, so linear would work, or?
It was one of the discussion points that we can talk more about that. But yeah, it's not necessarily that to be linear. Yeah, it was maybe the naivest and very, very simple solution just to updating the word vector based on the parents code.
So is the first word that you start with the first word of the document, then you go all the way through to the end of the document?
Yeah.
Okay.
But it's not necessarily that it will continue from there. I mean that from the third word, it will join to the most correlated word.
I mean, it's not sentence like,
yeah.
No, it's just the document entirely.
And here we have the second algorithm, which is very similar to the previous one, but in here, this line is added. The word vector is updated, and the updated word vector is joining to the tree. Then the parent's word vector in the next step is the updated word vector from the previous step. And at the end, to presenting the document, we are taking average of all the words in the document. Here.
Sorry, does it like if you apply it for all of the words, don't it like try to make all of them the same, so lose the meaning? If you run it infinitely, then because you're trying to update it, based on the difference between the two. So you do it multiple times. What happens? They're getting closer and closer and closer. So if you do it infinite times, they will like all of them will reach to the same limit.
Yeah, that's exactly the point of this algorithm. We assume that in here, we assume that if we make them closer to this domain and these closer to each other, then the classifiers should work better.
Right, but I mean, when do you finish your updating? Because if you do it too much, then it would like add unrelated structural problems to it.
Yeah.
For example, in a domain, like for example, politics. Yes, we assume we have a cohesive set of vocabulary. Yes, vocabulary should be close to each other. The idea is, for example, when we have word vectors in politics should be closer to each other than others.
Yeah, that makes sense. But what I say is that you, for example, run it like infinite times, then all of them will try to, get too close to each other.
Not necessarily, because we have different branches. Yes.
So
Because this is a tree, yes?
Okay, so we have 1 point.
Yeah, but for example, but you can, one node can be influenced by the root, by different measures, yes? Because this is a tree, it's not like, the example was a line, but it's not necessarily a sequence. Is a branch, kind of branching tree.
And we are updating the word vectors for a part of training data or for other training data. We are first splitting the train and test. And here for scalability, we just using a part of the data, which will we talk more in the results. And training and updating the word vectors for just this training data, and then using these updated word vectors for the testing data and for training data for representation. And then going to the classification task for evaluating the new generated word embedding. Yeah, okay.
Okay.
Moment of truth, the results.
Hold on. I lost you.
I think you are done.
Yeah, can you turn that on?
Yeah, the results. As I told you, we used the classification for evaluation of this approach. Then in this study, we used two data sets. One is IMDb, the famous sentiment analysis for the sentiment analysis task, with 25,000 training observation and 25,000 testing observation, and the unique words was 114,000 unique words in the training and 99,000 unique words in the testing. And the other was hate speech identification, originally with 3 classes. We ignored 1 class and used 2 other classes. And the training size is much more smaller than IMDb, and somehow the size of the observations are equal to each other, and you can see that it's much more smaller data set.
So the classes?
Yeah.
For the classification?
Yeah, for the classification. Yeah, binary classification. The task was sentiment analysis.
Ah, I see. Good or bad, something like that.
Yeah. For the baseline, we just compared our approaches with these baseline. The bag of words, which is the here reached to 84% and 86% FS score macro, and the word vectors, glove, and doc2vec, which does not using the global knowledge or pre-trained vectors.
How are you aggregating the word vectors in those?
These are the pre-trained models that the word2vec was trained on the Wikipedia that we use, and the glove was trained on I think internet crowd data.
I'm just curious for the actual feature extraction for the classification. How did you?
Yeah, it was just for the averaging the word vectors for each document.
Yes.
And we will compare the results with these baselines. Okay, here for the IMDb movie review data sets, you can see here these are the baseline results, and here we have the CTWE, which applied on the word2vec and applied to the glove, and you can see that it increased something around 2% for the in terms of FS score macro. And for the other data set, HSI, speech identification, speech identification, for word2vec, you can see the result is minus. It could not improve the result, but with the glove, it was very, very slow. It's something around 1% improvement was achieved. The other study was on the decay factor, the value of the decay factor. And you can see that for the IMDb movie review, the decay factor equal to 0.5 reached the best result in comparison to 0.2 and 0.8, which means that taking the regular average works better than the weighted average for this data set. And again, in the HSI, we can see almost the same for the word2vec, and for the glove, Yeah, and for the glove as well, the 0.5 work better. Then it means that the regular average works better than the weighted average. The other parameter was the size of the seed data. For the scalability, we are not using all the training for all the training data set. And we use 5%, 10%, 50%, and we compare the results based on the size of vocabulary. Here, it means that we trained we created that context tree with only 50% of the training data, and then using those updated word vectors in the model. And the result shows that the FS score of the 50% works better than 5% or even 100% of the data. And for the glove, again, you can see that the 50% worked better. Very, very close. The results are very, very close to each other. For the hate speech identification, we can see that 50% and again 50% was the best result. Then we can see that this method works with a small part of data. Just updating a small part of data can work as well as the whole data set.
So when you use 50% for the seed, that means you're creating the taxonomy on 50% of the data, and updating the word vectors just for the words in the taxonomy. Yeah. So any word that is not included in a taxonomy will not have its vector updated.
No, in that case, we're just using the original value of the word vector.
So by that, it shows that having this taxonomy can have positive and negative at the same time. If you do it on all of the results, then it would have a negative impact on the accuracy. Is that the case?
You mean that because it's for both of the classes?
For example, imagine that you say that on 50% of the data it works better, but when you have it like 100% of the data, it doesn't improve, or even it has worse results, a little bit of worse results. So
we cannot say that the results are worse because they're very, very close to each other. But the point is that when the trees become very, very large, it will lose the functionality.
It will add noise rather than information to the system.
Yeah, we can.
But there is no how we can differentiate between the noise versus information, the taxonomy here. Do you have I
don't understand. Then with 100%, your FS score is better.
No, we're comparing these two numbers. 50% was.
I think that's you have to see the trend. You have to compare for 10% with 100%, 50% and 100%. As you mentioned, the tree is very populated, so almost unmanageable. And you use 100% of the seed data. I mean, you mean the documents or the
training data?
The tokens or the documents?
The tokens.
The tokens. 100% of tokens. I think you are right somehow, because somehow one word at the end of document that the queue can cancel the impact we got from because it's very, very depends on the geographic location of the document in the document data set. Yeah, you are right. I got your point. Yeah, it may cancel. When you continue, you examine one token, for example, Apple. A couple of times, Apple could be tree, could be company. When you let Apple appears a lot, you may lose that advantage. Yes.
So I was wondering about the construction of the graph, because it seems like there's some taxonomy that exists of words that connect to each other and have parent-child relationships, etc. So when you take a sentence and you want to update the word vectors for every word in that, how many words in the sentence do you take at a time? Like how far back do you go?
For the training and creating
yeah,
the taxonomy, for all
the entire length of the sentence?
For the entire of the training data sets.
Okay, but like per sentence, say you're if you're updating a word vector and you have just take a sentence by itself, are you going back the entire sentence and using that entire sentence to update that vector?
No, it goes back to just one word.
Yeah.
One vote.
Oh,
You know,
okay.
in-
Okay, because
yeah.
my question was going to be.
No, but just one vote. This is why, you know, we don't consider grammar, even you don't reset the algorithm when you the end of document, Mehran, yes? You don't restart. You just go, you know, blindly to the end of documents. Even we don't consider a sentence or the end of every document. Am I right?
Yeah.
You consider the corpus as a very, very long string.
Yeah.
Yes.
Okay.
Gives
Okay,
the
'cause my,
weakness actually.
my second.
And for each document, we are just taking the average of all the words in that document.
Okay. Okay, I've seen that reminds me of some other, not entirely segue, but with term extraction, we were seeing about getting context vectors, and they said that averaging a series of words that come between word A and word B works remarkably well for building up a context vector for a word. Just wondering if you could comment on how your method differs from that.
Just taking the average of the word vectors was the baseline that we are comparing the result. Yeah, and with updated word vectors, it shows that it's working better than the original word vector.
I didn't see the baseline thing in there recent tape.
Yeah.
Okay, and that was the bag of words.
Yeah, and word to bake and club. These two numbers are the original.
Okay.
Here you can see that these are the baseline for this data set. It's the baseline for the other one.
Okay.
So question over here.
Do you have, you might be covering this like further ahead, but do you have an example of something that was misclassified before you apply this? So like an example that you've done the classification before and after. So do you have an example? Because I'm just trying to understand like how this could be like applied in the sentiment analysis context. So if it was like doing classification, it's me, I can relate, I can like make up examples for myself, but I'm having hard time to see like how this worked, like if you had an example of before and after, this was misclassified, but this was picked up like correctly when we applied this algorithm.
It's a very good question. The point is that in this study, we just analyzed the evaluation of the classifiers, but we assume that the words with ambiguity, for example, in the IMDb data set, which all the terms and the vocabulary is related to the movies. Okay, the words with vocabulary with ambiguity are their vectors is going to be changed and they will be matched with the context. Yeah.
You see, the objective was not sentiment analysis task. Sentiment analysis task was just a tool to evaluate a hypothesis. Hypothesis was, okay, we want to use for any reason because we are lousy or we don't want to use very, very expensive machine. We want to use pre-trained word embedding. Yes. Okay. Now the point is when you use pre-trained word embedding, you lose context.
Yeah, of course I understand.
Okay, now it's just a little bit, you know, the point is just one drop of context can give you this advantage. Not sometimes very, 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 marginal, but I have, in the discussion, I have more thing to add. But you are right. I mean, but the focus was not sentiment analysis. This is why Mehran cannot show you. For example, here we lost. We misclassified, for example, positive to negative sentiments.
Comment on the computational cost difference between word2vec and glove. So word2vec has a 300-dimensional vector for each word, right?
Yeah.
I forget what glove's dimensionality was for each word.
This one we used exact same.
Okay.
300
but
and 300.
In terms of performance, the results are very comparable. At least in the previous slide, if you look at the F scores for each. But was there a difference in computational cost?
Algorithmically, they're not that different.
So essentially, the knowledge encoded in each of the pre-trained vectors are very similar, even though they were trained on very different text corpus, right?
So not exactly. So sorry, if you want to take that. Word2vec has a very local representation. So you have this sliding window that you slide over your document, right? So if a word is over here, you're not going to be able to capture the relationship, although that word could be very relevant to the word you're looking at right now. The way Glove does it on a high level, it looks at the entire document. It still creates the word-to-word matrix, and then samples, and that's why it's efficient. Because the bottleneck before word2vec and glove was that you end up with this very big sparse matrix, and then you need to compress it, and that's a bottleneck, right? But the way glove gets best of both worlds is that it samples from the word-to-word matrix as opposed to sliding windows per se.
And I also want to add one more thing, which is that both of them, the word2vec and glove, they're just training one time, and then we can use them several times. Yeah.
Can you elaborate on the sampling method on the glove?
I don't remember the details and the specifics. No, I don't remember the details. Yeah. But you can think of it that it could be very big, sparse vector, and you may have one way to choose portions of it. Yeah.
Okay, these results are not included in that study and in that paper. This approach was one of 4 approaches I presented in my PhD thesis, and these results are the extended study. Actually, I just brought here just this method, just this specific approach. And as you remember, I told you that we just use one SVM classifier for this approach. But here we can see that we use a range of classifiers from the logistic regression, SVM, naive-based decision tree, random forest, KNN, and here we have the deep learning-based approaches, which are, most of them are the vanilla architectures. One-dimensional CNN, LSTM, deep CNN, LSTM, ADV CNN, and this tuned version of ADV CNN. And we use these word vectors as the embedding layer of the deep learning approaches and as the input for the traditional classifiers up to here. And you can see that for the IMDb movie datasets, here we had a binary problem, binary classification problem. This method improved the results for the non-deep learning approaches. And using this approach as the embedding layer just improved this LSTM architecture. For the other one, for the HSI, again, you can see that it works more better than here. And on the other data set like 20 News Group, Reuters, and AG News, you can see that some of the other classifiers shows improvement. For the AG News, only these two classifiers which I highlighted shows. Then it shows that this approach works more better with traditional approaches in comparison to deep learning approaches. And here we use the word-to-vec, just updating the word-to-vec. The next slide is showing the glove, which is the modified version of the glove vector. As you can see here, again, on the IMDb, it works better, and in HSI works better, and on these three categorical data sets, we can say not always getting the best results. And one more word embedding which added to these experiments is the fast text. Again, we applied this approach and using the fast text word vector and updating the word vectors by the CTWE. And again, you can see that this approach works better with binary data sets. Actually works for binary data sets better than the others. And this specific approach could not work very well for deep learning approaches. Maybe one reason can be that the deep learning approaches, I can say or assume that it's not very related to the embedding layer. We can discuss about that. That using the pre-trained vectors, how much it's effective on the performance of the deep learning approaches. For the summary, this CTWE or content tree-based approach benefits from the models which embed the global knowledge while localizing the updated word vectors for each local data sets, and achieved results achieved results showed an improvement in FS score for word-to-vec based and glove-based approaches in the document representation. For discussion, we can say that in comparison to bag of words, it's getting benefit of the word vectors, which the dimensions are reduced dramatically. And in comparison to doc2vec, which is not using the pre-trained knowledge and pre-trained model, this approach is much cheaper in terms of complexity, because the doc2vec should be trained for each document and every time it needs to be trained. And the weak point of this approach is that the route is selected randomly. And if you remember the formula, it shows that the route is really important, and its word vectors will influence all the new updated word vectors.
Yeah. Getting back to the comparison of the deep learning and classical ML method in your approach, would it be safe to say that the word-to-vec and glove are able to capture the nonlinear relationship between in the embedding space? So that's why
they're linear projections.
Yeah.
They're bilinear.
How about the sampling? Like, I know that it's gonna be word to word, represent. It's gonna be a sparse matrix, right? But if you're doing the sampling, if your sampling is non-linear, maybe that's the reason, if, as we see here, they perform a lot better on the
Sampling could be noisy, but it wouldn't render non-linearity, right?
I don't know what the sampling method is. I mean,
I'll tell you later.
okay.
I have to look it up.
Okay, why not just start discussion with this table? Why we don't, we don't see very strong results? It's it's a little bit too late to roast you for your exam. No, I have a point. Don't worry. Yes, okay.
Yeah.
But even I go back to the point that I mentioned about the sentiment analysis. I think that's also a reason why it's not because the content that the reason why you're doing this also matters. If you wanted to if keeping the content was a big deal in terms of the classification that you're doing, I can see much more improvement in the classification.
Okay, the reason is okay. Look at the sentiment analysis data set. The vocabulary is a subset of whatever pre-trained data is. You see, if for example one thing Mehran could do was, for example, pick a very specific domain, like for example legal domain. Say, for example, legal domain is very standard, clean language, and very cohesive. Vocabulary is it's a big part, a small pocket in the space. Or for example, healthcare data. Yes, the problem was not your method. The method was good. I mean, the data set you chose was almost the same vocabulary. Yes, only smaller. Yeah, for example, look at Reuters. Talk about art, politics, economy. It's exactly the same in work-to-work pre-trained data. Yes, it's Google News or Wikipedia or Google or web crawling. It's a very. But if you pick, for example, very specific domain, which is vocabulary is very cohesive, you would see much better result. Because capturing context is very important. You see. And I think this is the point. I think all these 5 data set almost a subsample of your vocabulary, and still you will see improvement, but not very strong. We cannot claim very strong victory because the data almost vocabulary are the same.
Like other ways to build this taxonomy so it better captures that information? Because what I understand is that you try to impose a global structure like a tree or a graph or something that tries to capture the relationships better. So have you
I have 3 points. Every paper, especially in this paper, you have to examine 3 issues: stability, scalability, and validity. First of all, my question is, do you think your algorithm is stable or not?
You mean the experiments are repeatable?
No, it's repeatable. But every time, if you scramble the documents, you will reach completely different taxonomy. Am I right?
Yeah.
But does it have impact to the result or not? I think you have done this experiment.
Yeah, it should change the result, I guess.
Is it dramatic change?
No, not very, very.
It's not dramatic change. It's not stable. It's obviously, yes. But this is why picking randomly the root doesn't have any impact. The only thing we wanted to try to have some not taxonomic relationship, some context. I suggested we should name this approach context embedding. Everything being embedded right now. But forget it. But this we wanted to embed the context in the kind of wherever a term appears in the document.
So this approach could be different, but for example, imagine you have Word2Vec, which has this fixed window size and going through the text, and then you change it to different window sizes, and then you will get different embeddings, right? But if you have larger window sizes, you will capture the larger like the thing that this taxonomy proposes. You will learn.
In another project, actually, Mehran was involved for entity extraction. We did the same. Yeah. And what about the scalability? Do you think your algorithm is scalable? If, for example, we go from, I don't know, for example.
Yeah, the algorithm to generating is following the N2, and
yeah. No, for example, I increase, I double the size of data set. Mm-hmm. How much does it change? I mean, generating that taxonomy.
Generating the taxonomy is following N2, then it's N square.
This is the weakness of this idea, because we won't create actually taxonomy. If we create taxonomy, because of the Zipf-ian distribution, adding double the size of document doesn't increase the size of vocabulary that much. Yeah, but this is because we don't care. We start from the first word in the document data set to the end. Of course, this it changed increase the complexity of the algorithm.
And there is another point that how we are evaluating these word vectors. There are two different approaches. Here we use them as the input to another system, which is looking at them from the outside, and it's something externally. But there are some other approaches which are evaluating them internally. For example, the distance between the conceptually related words. Yeah, it's another approach. Maybe one of the reasons that the results are not very big.
Point is validity. You test validity of the algorithm using classification. Why you chose classification? Why, for example, other NLP tasks like entity recognition? There was any reason, or just it was handy?
It was related to the availability of the data and the data sets that we used here. Yeah.
For example, if you use that for entity recognition, most likely you will see much better distinguishing results, because, for example, apple and apple, it may appear in document, yes, yeah, or case and case. Yeah. Case as a legal case, or case as a, for example, a case of a kind of a box, yeah. And that because the main reason in this paper was we wanted to resolve a very important problem as disambiguation. But the way we showed disambiguation resolution was not very, we cannot claim we solved the disambiguation problem. It's a classification problem, yeah.
So a couple of points. We have a question online, but before that, it was asked that like what the sampling method exactly was, and it appears that it was exactly as I said. It you stochastically sample from non-zero elements of your word vectors inside the word-to-word matrix. I don't assume it adds noise, but we can argue after. But it adds noise, but I don't think it adds non-linearity. Because for non-linearity, you have to be able. So like a sigmoid function would add non-linearity, right? So things that could be very negative could end up being positive in the next layer, right? Okay, no thoughts. So
yeah, I'm good.
I just want to give you a chance to. But let's go to the online question. So they say Soroush online asks, "Hi there, sorry for my misunderstanding. Not a problem. How the decay factor is calculated? Is it algorithm dependent or dataset dependent? If it is dataset dependent, how to define it for an unknown data?"
We are not calculating the decay factor. We're just defining that and set that as the fixed number. Yeah.
It's a given. This is why we
tune that for different.
It's a good idea to tune that one, but too many parameters.
So when you talked about, and this is my last one, and then I'll let you go. When you set up the problem, you started talking about things being mixed up, right? And that speaks to the nonlinearity issue raised earlier, because if it's all linear projections, as Word2Vec and Glove are, then obviously you end up being in the same like a similar space. Also, the words that you're representing, you are not distinguishing between two different occurrences of those while building your Word2Vec or any other representations. So how does it actually? How are we actually solving? Because I know there are some work tackling that issue, but are we actually making context dependent word embeddings? We're not here, or are we?
This is the motivation. We want to build context-dependent word embedding.
So, and it is such because you're updating based on the IMDb datasets, for example. Okay, I see. Then my last question would be, how does it relate to Elmo, for example, where you have embeddings and then you have context parameters, which would sort of distinguish your embeddings per your context or a type of corpus?
LMO should be trained for each corpus, yeah. And it's, if we want to compare this with LMO, it's much
another PhD.
Actually, it's much more cheaper. Just updating the word vectors in comparison to training that complex architectures. Yeah, and remember that this study was done in 2015, and that time there was no LMO, no, yeah.
So it's the father of Elmo.
Yeah.
The question I had was, what was the hyperparameter that you chose for the correlation to define the taxonomy? You tried different correlation ratios, for example, if 70% is a good enough ratio, or like, how did you capture
No, it was comparing the correlation between the vector of the word vector of the word which wants to join to the tree and all other word vectors which are already on the tree, and then pick the maximum and joining to that word. Let me bring you an exact here. Here, assume that I have a new word that wants to join to this tree. It will compare the correlation between the vector of the new word with all of the words in the tree, okay, and find out which one is more correlated and then joining to that. There is no threshold.
Yes, you know how when this taxonomy ends, if you go for example, the last word, you should try to check it with all the previous words.
That's why it's following n square.
Yeah, and going further is becoming more expensive if you add more words and more expensive. This is why just he used a subsample of the tokens, not necessarily the whole tokens. Why do you use the knowledge graph, for example? You know, like for example, not even for example, WordNet as a lexicon graph.
Yeah, it was another option. But the creating and using the human-made taxonomy is very expensive, and this approach is automatically generating even a big structure, but it's automatically generating that.
So there's a question online. They ask, has the CTWE approach been tried with multi-class classification to see how it works there?
Yeah. Yeah, all of these 20 news group with 20 classes, Reuters with 74 classes, I guess, and AG News with again 4 classes.
Those are what are the classes? Different intensity of sentiments, or what are the classes?
This one is it's topic.
Topic classification.
Yeah, topic classification. Yeah.
No, IMDb sentiment. Just only IMDb sentiment classes.
IMDb and HSI.
HSI.
Yeah.
The rest are topical.
Yeah, these 3 are.
What does HSI stand for?
Hate speech identification. Yeah, the original dataset has 3 classes, but we ignored 1 class to make it comparable with IMDb.
You go one more time to the previous slide. You were just on the taxonomy.
This one?
2 more forward.
Yeah.
So could you just remind me one more time? So for sincerely, on the right there.
Yeah.
Is it just going to be using the word vector for hope, or is it going to be using hope and everything above hope?
Automatically, this is the case. Yes.
Yeah.
Because inherited all to the top. Automatically, because hope is inherited some genes from give. This is give.
Yes.
I cannot sorry.
Yeah.
And then consequently to go to the root. Yeah.
Yeah, and it's one important issue is that when sincerity is joined to the tree. Yeah, for sure it was maybe sincerity was the first one, and then the hope is joined to that.
But maybe through this.
Yeah.
It makes sense because we assume sincerity and hope in word embedding should be close to each other. Yes, and this is why we just link them together because they are close to each other.
Isn't that case because they were like close to each other because of the different aspects they have? For example, see and hear and give are all verbs, so they were like closer to each other. But given hope and still hope, or I don't know, with chance, they have like these different aspects. So we got maybe like having multi-relational sort of
multi-passage. Yes.
Yeah.
I forgot, Mehran, when you compare, you calculate correlation between sincerity and hope. You compare hope, updated hope vector, or
with updated.
Updated
hope.
Have you tried original hope vector?
No, because we were losing all the assumption we had for this approach.
I think I just follow up your question.
Thank you. Would there be another way to perform this with relying less on the order of the words in the sentence? Just looking at what are within a sentence, what are the words that have the connecting words to their most similar words, regardless of because here you're starting from the first word of the sentence. Is that correct? Or how can you remind us how you're getting the root?
Yeah, but this method that you are talking about will lose the grammar, of the document.
You already because does grammar really play into this though?
The order that the words are joining to these 3 make it different. Yeah. Then I can say that grammar is.
I guess the documents are several sentences long in IMDb.
Yeah.
Should be short documents.
Yeah, they are short. Usually they're just a review and
review.
They're not too large.
Movie reviews.
So, I remember an interesting paper from 5-6 years ago. They showed that I don't exactly remember the task, but they showed that adding random binary trees would help. In general, across the tasks that they tested, would just increase. Just random architectures, like no grammar at all, no parsing. This could to some extent also relate to that. Although there is a little bit of intuition over here, but so maybe as a next step, I was wondering how much actually using more informed linguistic trees would help. Like let's say make a parser, or does that, or make use graphs that are already we know that are intuitions, or
Yeah.
maybe category along one of the other points that was raised earlier. What if we detect not randomly group everything together, but do some operations for verbs, some other ones for nouns and adjectives?
Yeah.
I was wondering, just give me more structure.
Yeah, and let me share you something else, which after this method, we worked on one more advanced method, and right now that's under review for publication. And the other one is solving the problem of choosing the route. Yeah, in the other approach, we first generating one fully connected graph from all the words, and the edge between each two nodes is the correlation between two words, and then calculating the summation of the edge for each node, and the node with highest summation of the correlation with all other words is chosen as the root, which is the word which is more related to all other the words. And then by using that root, we try to create one tree from that fully connected graph, which here we use the Krauskal algorithm for the maximum spanning tree, and then updating the word vectors based on that, and we reach much more better than results we have here.
You did another kind of experiment here, I think you forgot to mention, and instead of word embedding, you used random embedding.
Yes, yeah.
And even using random embedding, adding context shows some promising result.
Yes.
But
yeah.
you didn't have in this
no, unfortunately, I do not have the
just
random embedding. Just one random vector generated and then compared with the word-to-vec glove.
Means purely we just get the context, yes?
Yeah.
That was very nice experiment.
It's happened quite a few times in NLP, like back in the day when people were testing parsers, or the best NLP school was the one with the best syntactic parser. I think Colin, he's now an NYU professor. Christopher Colin, if I'm not mistaken, he created this very similar parsing structure, but he called them, I think, headed trees, or head phrase parsing, something like that. I don't remember exactly, but all he did was for each leaf of the graph, it would add the head itself to it. So it would have just that as a distinction, and then it would just perform better. Which at the time seemed redundant to me, because that head is already there in the tree, right? As a root. That's one other thought. The last thought. Recently, we had a talk in linguistically informed self-attention networks, and that also showed that these self-attention architectures supposedly do, to some extent, do similar things as you did over here. So every word is a weighted average of every other word in the sentence. And they showed that even then, when you add a submodule of the architecture, only trying to learn the grammar, so what is verb, for example, would increase across quite a few, would increase the performance across quite a few tasks, which also I think is parallel to this one, which adding architecture and structural information can usually help.
Thank you.
Why having this assumption that we only have one context, we should only have one root, which all of the words should be tried to get closer to that one root. Why do we have such assumption? So maybe there are like 2 to 3 main words which are like representing the topic in here that we try to get each of them representing to that, closer to that main word.
Okay, it was very interesting idea because in another approach we used some clustering, and by applying the clustering on the word vectors, we found some centroid, and then representing each word by the distance to that centroid, and it was another approach.
They use the Chinese restaurant algorithm to find those clusters. They call it Chinese restaurant. And actually, you tried that one as well.
Yeah.
Was it better or worse?
Actually, all of them was better than this. I should
You had the
confess,
most worst product. You see. Thanks for your honesty.
Yeah. Actually, to be honest, this is how my study started. It was the first one, and then after that, we should all the other approaches was better and better. And yeah.
There's a question online asking how did you tune the hyperparameter? I assume they're talking about the decay. Decay factor.
Yeah, it was, as Dr. Makrehchi said, it was a free parameter. We did not tune that automatically or training the data.
Or what type of search, perhaps?
No, we did not do anything. We just used
those 3 values.
Yeah, just those 3 values. Yeah.
The good news is that it doesn't have any parameter setting.
No.
That doesn't have any. Just one free parameter. That's all.
In general, very computationally low cost. It seems like.
In terms of tuning and parameters, yeah.
It depends how rich are you. But it's just offline, yeah?
Yeah.
Offline. You do it once for that domain, and that, maybe it's time to time you have to update it.
Okay, so thank you very much, guys.